happy that Jumbo is visiting. He's a professor at UPenn, and I guess a lot of people here actually knows him well. And one thing I want to mention is about among all his contributions to the community. One thing I want to mention is last year at CVPR, his paper on normalized cut won the Long-Higgins Prize for a contribution that stand the test of time. Okay, Jumbo.
Yeah, thank you, Thomas. Yeah, it's great to be here. I guess know many of you here. So, and actually, I should thank Thomas also. Thomas was a wonderful office mate for 4 years at Berkeley, and contribute to many of our work that we've done together. And it's great to see him here also. So today I'm going to talk about some of the work that we are doing at Penn. The title of the talk is Simplified Visual Recognition with Contours. So I'll make that topic a little bit clear. So usually when I give a talk, I want to have an understanding who my audience are. Even though I know quite a bit of you, I want to see what you see in images. So here's a illusion. How many people actually seen this illusion? Okay, few. Okay, so what do you see immediately? For people who haven't seen, what do you see immediately?
The girl facing that way.
There's a young girl facing that way. Okay, how many people actually seen a young girl here? Wow. Okay. And there's actually an old lady here. How many people can see old lady? Wow, I've seen it before. Okay, so if
the only lady over here.
so, yeah, I see. So if you just kind of cover the little dimple here, you can see that's the nose of the old lady. That's the mouth. That's the chin, and that's her eye. Can people see it? So usually I go around and ask that question. So at CMU, when I give this talk, everybody saw the old lady. Nobody seen the young woman. So elsewhere, I think it's Pittsburgh, yeah. I was in Princeton, Maryland. Everybody seen a young lady, so it's Penn. But CMU people really just see the old lady. Yeah. So now I know who you are. I can start. So this is actually a bit of a motivation that this is an experiment that we're doing at Philadelphia. This is a project on people detection in the dynamic street scenes. So the problem is that you have a car that you're driving down the street. So this is a street in Philadelphia. Fernando knows well. And imagine that we have some impoverished LiDAR data. So this actually comes from stereo. It's pretty bad, but it gives you quite a bit information. So those are, you can see these are traffic lights. And this is an individual that's moving down the street. There's a couple kids coming into the field of view. They're playing on the street. And you see the stereo is not great, so sometimes we lose the target. Sometimes we get it. The goal is eventually to be able to detect people as we move across the scene. And not only that, segment it out. And the reason we want to segment it out is also we want to get a precise pose for those individuals to understand what they're doing. Okay, so this is a challenging problem, but we are trying to using motion and LiDAR data to help us to solve this problem. So just to give you a little background on this project, this is our little band, so I'm advertising again. This is our band that participated in the Urban Challenge that we finished number 4. So it's not in the news, but I'm just very proud that we finished 4th and with almost no funding. So we add a little bit of camera to us. We add 2 stereo camera on the board. We have a Ladybug, which is from Point Reyes. It does have many laser scanner on the car, but the laser scanner is pointed to the ground. It's not looking at it any distance away. So mostly looking for obstacle. What we're looking for are people kind of far away, 40 or 50 meters away. So when we first took this car out, and it turns out Philadelphia is cold, and the camera freezed up, and all the synchronization circuit fails. So we spent the whole afternoon, and all the data came out bad. So we had to redesign the circuit, make sure it's temperature proof, and we need to plan the collection, make sure the temperature was above certain threshold. Quite a bit. We also calibrate the synchronization down to very precise measurements. Okay, so we took this little band and we drew around the center city in Philadelphia. One loop around the university, one loop around center city. The temperature, as you see, is about 46 degrees, so that was good. We took about 1 hour's videos, total 6 miles. The resolution is indicated above. So this is the video that we took. A part of the video we shot. Again, this is for people who know Philadelphia. This is Rittenhouse Square. So it had 2 stereo cameras. They're synchronized exactly. On top of it, actually has a ladybug, so actually you can see it's 360 degrees. But we're primarily using this stereo images to detect people on the street. So actually, one thing we found very strange, actually, or a little bit surprising, is actually we're thinking that we have this funky car driving the city, that people are going to stare at us or surround us. I mean, Philadelphia, no one cares, so we're driving around. So here's a bit of problem of dynamic range. The camera has a fixed shutter speed, so we had to manually adjust the dynamic range as we drive. So it's a busy street, a lot of people, they're often including each other, and there's lots of moving objects. So the goal is trying to detect those people on the street. Yeah. So we have a natural advantage because we're in an urban environment, so it's easy to take those data. Let's see, so no more chairs. Apologize. So you can see actually there's a lot of people standing at the bus stops. They're just reading their books and don't even pay attention to us at all. So it's great. So we actually feel. So this is the sequence we saw earlier. Okay. So when we got this data back, we immediately run a stereo on the system, and you can see stereo is not great. Actually, it's somewhat reasonable. So blue means kind of close, and red means far. It's not great, so we decided, okay, we push ahead anyway because we have a project to do. So we actually ran Jean-Yves, where's Jean-Yves? Jean-Yves said, we did by stereo code, we calibrate the camera, and he has a triangulation software. We run a triangulation software, and it looks pretty good, but kind of crazy looking. It's not his fault, it's our stereo disparity fault. So we decided to push ahead anyway. And what we decided to do is actually do some very simple grouping of the 3D point clouds. So this is actually just taking the 3D point cloud. This is disparity map. And we did a very simple sort of adapted region growing to abstract 3,000 blobs. From the 3,000 blobs, actually you can delete quite a few blobs because they're the wrong size. So for example, if a size is too big. So actually we're able to clean up the data quite a bit. So this is the data before in 3D, and this is the data after that. Okay, so this is just simply doing connected components and threshold based on size. Because you know that people are a certain size, they are not in the air, so you can cut off, figure out where they're on the ground. So we are using it as a sort of a cheap imitation of LiDAR. It's also important because we need to detect people kind of far. So this is actually pretty close. This is meters. It's about 30 meters. This is 35 meters. Okay, but the camera can see pretty far. So this is, again, just an illustration of what we got. So again, this is just an image superimposed on the bounding box. The bounding box are those objects that fits in 3D, those criterion we set up. So there are good detection rate, but lots of false positives. Okay, and we're not using the motion, so we have intermediate sort of occlusions, and we lose the target quite once well. So this is individual that walking across the street. Let me just play the video again. Okay, well, this is a longer video. At the beginning, if you're fearing the MATLAB has trouble, so after that get corrected. So this is again a shot on the right-hand side is the stereo plus the cleanup version of stereo, and the cleanup, what I mean is basically extracting human-like blobs in the stereo set, and this is superimposed on the regular image, and this is a disparity map. So you can see the individual popping out quite well once in a while. But we lose them sometimes. So this is a pole, I think. Let's see if there's a pole come in. So that's the individual come in. Okay. So in general, we were doing all right. I mean, in terms of using the stereo and the image together to get a very good hypothesis on where potential human targets are. But as you can see, there's a lot of false positives in the set. And the idea is trying to use the image analysis or vision to remove those false positives. So those are the list of sort of true positive on top, a false positive below. Okay, you can see there's a lot of pose variation. We didn't quite expect. It turns out a lot of people sitting on the street. We didn't expect that. It was, it was not our expectation of a pedestrian. But there are many of those, and people that do get occluded. This is get cut off because the camera is tilted high. Those are the false positives that falls into the category of people looking like 3D point clouds, meaning that skinny, kind of elongated, vertical things. So those are the things that we need to get rid of. Unfortunately, the image recognition, most of the softwares have failure modes on exactly the same type because they're exactly skinny, long, cylindrical-looking objects. So the rest of my talk is really motivated by those examples. We want to use find out vision softwares that can delete those false positives. So I won't go too much about pedestrian. Just want to show you that this is the pipeline that we're going to work on. Essentially, we're going to have some training examples here we only use about 20 pedestrian training examples. We have examples, and we have silhouette of those examples. And we want to detect them and want to segment them. So people ask me, why only 20 pedestrians? Right? Most people, when you look at the training set, they're talking about thousands. So if you look at the typical training set for pedestrian detection is about 2,000, 3,000 training set, about 1,000 test set. Right? So what is happening actually, if you look at the training set, is trying to learn actually the negative example, which tell you that's a building, that's a trash can, that's not a people. We actually can show that with only 20 people, we can cover the most of the people pretty well. So in a sense, the body are compositional. Right? You could have somebody's head, somebody's lower body. Right? It might not be a perfect match, but when you take somebody's body parts, you actually can glue into any arbitrary persons. So the 20 actually is more than sufficient to cover pretty much any post variation you have. All right, so I'll start talking about the sort of the research behind how do we do this, and I'll return to the people detection later. If you have questions, just feel free to stop me. Okay. So the first part of the talk, I'm going to talk about contour grouping. So why contour grouping? So the contour grouping is motivated partially by the pedestrian. People are sort of defined really by the shape. It's not really defined by the color shirt or the texture of my clothes. There's no texture of my clothes. It's really the shape. So, for example, look at a horse. A horse is another animal which are like human in the sense that they are defined mostly by the shape and not by the texture. So on the left, you see the image. On the right, you see an edge map of the image. Right? So you can see the edge map actually looks pretty bad. But I want to point out actually in those edge maps, there are good stuff. Only thing you need to do is to delete the wrong stuff. The image will become much more appealing. Okay, so on the right here is just simply the same edge map on the left with junk removed. Okay. You can see a very clear horse with the leg, the hairs, and the body parts. Okay, so the information is in the edge. So people shouldn't forget about edges, and the information is indeed there. Okay, all you need to do is somehow able to extract it out the clutter, and pop out the foreground. Okay, it's there. So, and if people who are not convinced, I want to quote the famous psychologist Kafka says, "Long contours are just nice to look at it." Okay, no one laughed. Okay. All right. So a lot of my work is inspired by a long list of good people who have worked on this, and I typically want to give credit to the two authors on top, Ullman and Shashua, who look at the salient structures, and Muhammad, William, and Thornberg, who look at the segmentation of a contour. Many of the ideas actually came from those two papers. But those papers below also I talk about contour grouping. So what makes contour grouping very difficult? So here again is the image, and on the right is the edge map, right? The snake is in the edge map. All we need to do is clean it up, right? It's not an easy problem because a lot of clutter. Okay? The clutter is number one problem, but that's not the biggest problem. The biggest problem is when you have a salient contours. Even with the salient contours, you tend to have a gap. Okay, gap is due to in this case the hair on the horse, but could due to illumination or whatever condition you have. So you may have very salient contours, it might have a gap, right? So make it sort of connect the components, make it very difficult to run. So gap plus clutter makes things difficult because with gap you had to jump, okay, to connect to the other part of the contour. But when you jump, very likely you would jump into the clutter instead of the right contour. So how do you know you jumped to the right place? That makes the problem very difficult. So before you want to say, that's a difficult problem, I want to show that this actually can be done. This is the output of our systems, where again you see the black and white contours, and the bright contours are the contour we are extracted as the salient contours. So those will be the basis that we're going to use for object recognition. So how we do this? So the way we're going to do this is again formulate the contour grouping as a graph partitioning problem with a slight twist. So here we have an edge in the image. Each pixel is an edge or non-edge. If it's an edge, you create a node. But instead of creating one node, we're going to create two nodes. Okay? Each node actually have a direction attached to it. So imagine each edges are sort of a slider. It's not a fixed node, it's a slider. So meaning that once you get onto that node, you're going to slide left or slide right. Okay? So you do the edge detection. You create edge pixels. For each edge pixel, you duplicate it to two sliders. Okay? So then what you want to do is create a connection between two sliders or two edge pixels. Two edge pixels which are curvilinear, meaning they're roughly in the same direction and they are sort of curved in the same way, are strongly connected. And two pixels kind of pointing at each other. Two edges are pointing at each other. They can't slide on top of each other. Even at the right configuration, they do not connect. Okay, this is a very important concept. Each edge has a direction, And only when you go from one direction to the other, consistent in the forward direction. So when I was giving a talk, actually, Andrew Zisman pointed out this is like Egyptian walk, walk like Egyptian. So you think of Egyptian walks. So you had two edges both point in the right direction, then you connect. If two edges kind of wrong direction, even the right configuration, you do not let things connect. Yeah.
So terminology, I get a little bit confused here. So you have edge. This is the little edge elements.
Edge elements, yeah.
They will be nodes, these directed nodes in the graph.
Right. There will be the direct rate
And then there are the graph edges.
Yes.
And those are other things.
Yes. The graph edges are denoted
Let's
by.
call them arcs here to make our life easier.
Which ones? This arc.
Yeah, those little
So
arrows.
okay. Yeah. So.
I'm just trying to make sure that I understand.
Right. So unfortunately, image got edges and graph got edges. Those are two different type of edges. So we can think of it as edge nodes are just, so I call it edge node because there are pixels which are image edges with different directions, and called the graph arcs maybe that connects them. So the graph arcs is defined by the connectivity of the edge direction. Okay. So two edges in the same direction, so edge nodes in the same direction can connect, otherwise not. Okay, so with a small caveat, each node in the edge map can also return, flip around directions once in a while with a very small weights. Okay, so this is small. Yep.
What prevents? Always most edges will be both ways you connect, right? Or probably you connect only one way, or you can connect.
So we have a very small weight basically returning. Okay, so most of the time it goes straight, but once in a while we'll return. Yeah, we'll come up to this point later. So when we have this graph arcs, then we're going to normalize it into a random walk probability. Okay, so for each pixel I, we look at all the edge nodes where it can reach. We take the sum, normalize it, so you have a random distribution, so random walk distribution. So basically, you going from each pixel, you have a probability going from this arc, sort of image edge, sliding to different pieces of the image contours. Okay. You can think of it as a probability that start with I, jump to J in one step. Okay, where the probability happens. You want to make sure you're able to jump gaps. So you're not connect only the nearby ones, but some pixels within some radius way, because there are holes in the contours. Okay. So the normalization has an extra degree of effect, which is that when you get to the end of the contour, you have nowhere to go. So you even have a very small weight to return to yourself. After normalization, this return weight becomes normalized to 1. So it becomes a very large probability to return. So the end of the contour, you have nowhere to go. You have force basically with 100% probability to return on the same path. So now essentially in the image, you have open contour. Open contour meaning a straight line. This becomes a cycle in the graph. And if you have a closed contour, traditionally closed contour, you still have a closed contour in the graph, except the two copy, one clockwise, one counterclockwise. Okay. So in any case, we unify all the contour into a cycle. Okay. To find contours, open or closed, you just look for cycles in the graph. Okay. After normalization, every contour becomes a cycle. Because open contours, they had to cycle the end because probability 1 had to return somewhere. Okay, otherwise. Yeah?
So if you have such a high probability of returning back, in the second case where you have the closed contour, will there not be a tendency to actually break that closed loop and just keep
cycle in the middle? Yeah, so that's why you have to very carefully choose the weights to be self-cycling back. The weight is small. But in the middle of here, you have large weights going forward, right? So the rate's return is relatively small. So it's normalized. It's only at the end point when you have nowhere to go that small weights become amplified. Okay.
So how do you balance that? So you have this small return weight, but then you also have weights that transition into clutter.
Right.
And so how does that pay?
Good question. Yeah, coming up. Yeah. So now the question is how do you find the salient graph cycle, right? So now you have a cycle to look for. In the clutter, as Fernando pointed out, you can cycle too. Okay, you can go to a contour, jump to a clutter, and you can cycle. You can always cycle. The question is how do you find a good cycle, right? So people study computer science will say, find the shortest path, shortest cycle. There's the longest cycle, there's the shortest average cycle. You can come up with many variations, the longest or shortest. The problem is we don't know the length of the cycle. We don't know how long the contour should be, right? We want a good one. We just don't want the shortest one or the longest one. or the average shortest or average longest. So we need to know the length of the contour. That's the biggest thing we need to find. So here's the concept I'm going to introduce. It's called the persistency of random walk. So what we look for is the probability of a cycle start with I and go through some other piece and return to himself at some time t later. Okay. So there's always a cycle that comes from I, go through this graph, sneak around, eventually come back to itself after time t. Okay. So we want to look at this property. So this is our observation. The observation is that if you have a very good cycle, or salient contour, then the probability to return to itself after time t can be seen as this plot, where in the x-axis is the time to return. In the y-axis is the probability of that returning happening. You can see with time very small, you're not going to return, because the only way to return is to cycle through some other guy. You can't return because the graph is directed. You can only go forward. The only way to return is going forward and eventually cycle back. So you cannot return immediately because you cannot. And then at some time t, which actually corresponds roughly the length of the cycle, there's a lot of random probability of returning. And then you're going to diminish. At the 2t, you're going to return again, right? Because the same cycle is going to happen again at 3t. So you can see this very nice rhythmic pulse in the probability of a random cycle repeating to itself if you're on a very salient cycle. Look at the background clutter. In the background clutter, it's basically a Brownian motion. Brownian motion just kind of randomly walk around. Eventually, it will come back to itself. But you can see the probability to return to itself is flat, because there's no particular cycle that had to return to itself with that period, because it can return to itself with an arbitrary path. So you can think of the path length to return to itself as uniform. Okay. So that's the first signal that we're looking for, that if it's a good cycle, then it has something called the persistency, meaning that it repeats once you get on it. Okay. So Fernando asked a question about clutter. So those are the clutter. So if you jump into clutter, once in a while you return maybe too early or too late. But by and large, you're going to return that period. So how do we measure this persistency or peakiness of sort of probability? So one way just simply measure the areas under this probability around t, 2t, 3t. Divided by total probability to return. Okay, so it's just the probability of a random walk return to itself, k times t divided by total time to return. So visually, all you need to remember is just this y zones divided by total area under the sun, the peak. Okay, so we want this peak to be, if this thing is peaky, then we want this ratio to be large, to close to 1. If it's a Brownian motion, this is going to close to 0. Okay, so the question now is how do we compute this, right? You can write a computer program to simulate the random walks, looking for the chance of returning. You can do that. It's going to take a lot of time, right? But that's one way to do it. So fortunately, we proved the theorem, which shows that the peakiness or time to return ratio is actually related to this nasty equation. Okay, this is never a good time to show an equation, but this is the equation I have to show once. So this equation shows essentially you can predict this R by this ratio, where the ratio is really dominated by the lambda, where lambda is really the eigenvalue of this complex. Actually, lambda are the complex eigenvalues of this random walk that we generated. Okay, it's a direct random walk, so therefore it has a complex eigenvalues and eigenvectors. And the time to return is only non-zero for a non-real or complex eigenvalues. If the eigenvalue is real, it's diminished to 0. You can show that. Okay. So now the question, do we have eigenvalues which are complex? So in fact, so those are the eigenvalues, the random walk matrix, looking for eigenvalues. And in fact, this is a plot of eigenvalues. In the horizontal is real axis, in the vertical is the complex axis. So each dot is plotting one eigenvalue. Okay, so you can see this is a complex one because it has both imaginary and the real components. So there are many of them, actually. So many of them sits on the horizontal axis, which are just real eigenvectors. Those are the ones that we were using before for region grouping. But it turns out there's lots of other ones we're not looking, actually had to do with contour grouping. So now we know that the eigenvalues are useful. The question is what those eigenvectors are. So that's a natural question to ask. So here's a contour. So let me stop the animation, or maybe just play the animation. So this is a contour that we selected the image. Okay. What we did is then plot out the eigenvector associated with each point. For each eigenvector has essentially the real value and the imaginary value, right? So each eigenvector is going to have a value x, and x has the real components and imaginary components. If you plot the real and imaginary components, it looks like a two-dimensional plot. So what we did here is then move each point along this contour and show what happened to that point in this imaginary space as we move along the contours. Okay, so what do we see? What do people see? So what I'm doing is moving this pixel up and down these contours. Every time moving, I plot a point in the complex space, which is the complex eigenvector for that pixel. Okay. You can see as we move up and down the cycles, essentially there's cycling around the origin. It's orbiting. Okay. It's like a planet going around. So in other words, that for every position in the image xy is translated to the complex space, imaginary space, where a cycle is actually a real cycle in the sense of a graph. Okay, so that's the key insight. So that's our conjecture. So now the question is, can we figure out what the ideal cost is? So the ideal cost within the conjecture is that what you want to do is not really, plot out such nasty looking cycles. What you want is a really nice looking cycles, but this is ideal cost. The ideal cost is that as we move up and down a clean cycles, each point should be put into a complex space such that it orbit around the origin. Okay, so why is that? The reason is that you can think of on the image, there's action on every pixel. The action of every pixel is translation. We can only translate a pixel along the contour because of random walk. We carry the pixel along. Okay, so in the image, there's action P that act on the pixel X, which is the position, XY position. In the complex eigenvectors, because the only thing I can do is multiply lambda. X is the position on this complex space. And the only thing I can do is action on this complex value. And the complex multiplication by lambda, it means what? Rotation. We can only rotate. So basically, we want to couple these two steps together, right? So every time we move in the image, I want to rotate around the origin. That's what the eigenvector is doing. Don't know if I can play it again. Okay, so as we move on the contours, I can move orbiting around. So orbiting around is essentially an action of multiplied by lambda. Every time you move multiply lambda, it moves. Okay, so now you find the equivalence relationship between the two. So now the question is, how do you distinguish clutter with a real contour? What's a good contour? What's a bad contour? We conjecture that real contour give you a very large orbits in the image in the embedding space, and the bad clutter has a very small orbit or orbit close to zero. The reason is we conjecture that for the clutter, on each step, you have multiple neighbors you need to go to. Okay? You can think of it as a very large set of things you need to get to. And when you have a very large set of things to go to, the radius shrinks. Okay? So at some point, actually, somebody pointed out this is a capital law of gravitation. The faster you move, you have to shrink the orbit. So you can think of in the salient contour, there's only one or two guys you need to go to, and therefore you need to only rotate a very small angle. So when you rotate a very small angle, you can make the orbit very big. So our conjecture is r times delta theta equal to constant. Okay, so meaning that you only have when you have a very clear idea who you need to go to, the orbit become big. When you get confused, you need to go to a lot of orbits. So basically, you want to be sure that the r times this delta theta is constant. Okay, so in this case, you have a small area. I mean, this is the same area as this area. Okay, so if you have a lot of guys need to rotate to, then the circle shrinks. So now essentially, we can write down the cost function, what make a good cycle, and involve the radius, theta, and delta theta. We can do all the math, which would basically prove that to ourselves again. The way to optimize this criterion is look at the left eigenvector and right eigenvector of the solution. So there's another theorem we can prove, or we can skip that again. So, but we showed basically eigenvector, yes, yet again, a way to optimizing this cost function of seeking a largest cover or largest cycle in the complex eigenvector space. So now we basically have the following solution. We take the image, we build a random walk matrix on it, we compute the complex eigenvectors, look at the eigenvector itself, find the biggest cover cycle in this graph. And this is easy because we do shortest path. We essentially find this maximum cover path, which is dynamic programming, with exactly the path length of 360 degrees, okay, in the embedding space. And that will extract out the contour for us. So let me show you some results. Those are the results obtained. This is the image with the salient contour superimposed. And this is the image with the edge map we extracted and the salient contouring we superimposed on this. So for you people are familiar, this is actually from the Berkeley segmentation data set. This is a snake. You can see that we actually can extract out quite clean in the contours. And this is a person standing into a building-like things, and the building are suppressed, considered more like 2D-like rather than 1D-like structures. Question?
How does this behave in the presence of gaps? I'm guessing there'll be breaks in the embedding space also.
So yeah, I guess I missed a little bit at the beginning. So at the gaps, random walk is able to jump some gaps. So it's able to so the graph has a connection radius of something, let's say 10 pixels. So it's able to jump ahead for 10 pixels. So the random walk will persist after some time. Yeah, good question. So this is more results on set of images. Again, the 2D type of like clutter tend to be ignored, and the line contours. It turns out that the human body are indeed have a lot of line structures. You can see she's wearing a dress, but dress is highly textured, but the background, I mean the boundary between her dress to the background has a very salient contour. Okay, so we're not running any stereo on it, right? But still able to extract very salient contours. So this is the goal we want to do: extract very long salient contours, from which then we can use for recognition or comparing shapes. Okay.
How many IT projects do you do basically some
Yeah, we picked 200, 300, I forgot exactly number. We didn't really look into very carefully because actually we are wasting a lot of energy in the sense that those eigenvectors come in conjugated pairs, that every eigenvector is duplicated twice. I mean, you should be able to hack into the code eigenvectors only looking for one set of solutions. But we haven't got to fix that yet.
What's the meaning of the conjugated pair?
They give the same cost function. So these are complex numbers. So those give you the same cost function to the. Okay. So this is some horse images. Again, those are the images with background clutters, and you can show that we're able to pull out contours. So we call this thing called untangling cycles. It's like pulling spaghettis out of a sort of very random mess. So long as a very clean contour, we can, no matter how it's zigzagged around, we should be able to pull it out. Okay. So long as it's able to detangle it, meaning there's nothing that kind of really hold it in as a 2D pattern. Okay.
Do any thresholding on the embedded space?
You all need to do thresholding. So because you can always, you can measure, actually we'll talk about this. So you need to measure the performance of the system. So performance system is when measured against human. So for example, at Berkeley, this is the Berkeley segmentation data set. You have images, about images. You have human label data. So human label edge is all the human label superimposed. Okay. There's some people who are labeled more, some people label less. So the ground truth is the superset, meaning if somebody labeled as edge, that's an edge. Okay. So that's a superhuman label. From that, you can look at the hits, meaning what you human label, what you also detect. That's basically telling you how much recall you have. You also have misses, which are the blue lines that what human label, you didn't label. Okay. And there's a false positive that you labeled, the human didn't label. Okay. So nobody labeled. Okay. So you can see, well, some of the false positives are reasonable, but nobody labeled, so we have to pay a penalty on this. So we can look at the precision. Precision essentially hit divided by false positive plus hits. Recall is basically how many real edges we need to detect, or how many we do detect. Okay. So we look at the precision recall performance, and this is the baseline these days. This is called the probability boundary detectors from Berkeley, PB. And there's two more global methods. One is using the CRF, Fernando. This is work done by Xiaofang Ren at Berkeley. The other one is by Pedro from University of Chicago. He has a method called minimum cover in blue. And our, you can see, is on top quite a bit. So we do better in the recall range between basically anything above 60%. We do worse, essentially. Actually, we don't do anything after 60% because we cannot group small contours. The contour have to be grouped together. So beyond at that point, we cannot group anything. So we actually don't return anything. So we cannot detect sort of small fragments. So again, you can ask, what are those missed recalls? The misses are blue lines. Okay, they tend to be, in this case, occluded by foreground objects. So there's a lot of high-level reasoning goes in. Somehow we missed it. Okay. Any questions? Yeah.
Is there a parameter or a threshold somewhere that controls how small is too small?
There's no parameter for small, too small, but in the random walk, you cannot find the salient cycles once it becomes too small. So because it can sneak around anywhere. So because the gap, it goes, yeah.
So that example is an occlusion example, right? There's a really good contour there, just like partially occluded.
Right,
The blue. So,
Right.
so now because you have this notion of directionality,
Right.
you have something which is kind of preferential direction. So if I can jump, if I'm going in, I can jump a lot more if I'm going, as it were, in a straight line.
Right, right.
Than if I take a sharp corner.
Right.
So if it is you're dealing with clutter, the things you could connect to are in different, pointing in different directions, and therefore you don't allow yourself to jump much, you let them walk.
Right.
Whereas in something that's straight, where you can jump exactly in the same direction and still hit another contour, another edge element, you say, okay, this is maybe not so bad.
Right. So this is a vision called the modal amodal completion. This is actually what Thomas has been working very hard for his thesis. So it's true. So if you know the occluder, then you should definitely connect the background together, because then you can explain away why they're discontinuous. You need a way of explaining away of the connection. Otherwise, if you just look at something that can have a big gap you jump straight into, then you're going to actually cause a lot of clutter comes into the question. So you want to make sure that you have a good explanation before you make this large jump. But this is actually something we're actively working on. We have actually a very good method to do this now. Under Cook, yeah?
Question in relation to your comments. Couldn't you use the direction of the gradient to add priors to where you should link instead of linking, instead of orienting the edges independently from the image itself? Couldn't you use, say, the fact that you know that the gradient, goes from bright to, dark in a certain direction, and use that as a prior to not connect edges that should not be connected, especially when they're disconnected?
Right. It's a good comment. So the comment is it can use polarity of the edges, dark to white to dark transition, additional. So we try to do that. We tried many different versions. Actually, this precision recall is not the first one. So some of them actually is below. I'm not sure it's the top is one. There's different parameter you can tweak. We haven't really completely looked into that yet. Yeah, it's a good comment. Yeah. Any other questions? So this is my essentially the first part of my talk. I blast through it pretty quickly. The idea is essentially we want to take an image, extract those long contours out, remove textures, remove sort of small pieces. Now those are the sort of basis for my recognition or detection. So I'm going to talk about that in the next step. So there's a couple more images we had to do. Okay. So the second part I want to motivate this example of where's Waldo. So anybody has a kids, I've seen this book. So where's the Waldo? And people see it, right? So so this is similar to my street scene, except a little more cluttered. Of course, you can find it, and the problem of finding where's Waldo is you're probably not going to recognize him by just purely or by color and texture. So shape is required. So again, I want to come back to this point of this illusion. And actually, this illusion I want to show, again, to show that the recognition is a whole rather than sum of parts. So in this case, when you see this woman, right, you really need to see the entire context before you can make any decision what this piece are. For example, this line has no meaning. Right? It could be a necklace, it could be a line, until you see the eyes and nose. Okay? The meaning of this line depends on all the context. That you can't. Basically, my argument is you cannot see the little parts until you see the whole. Okay, so that's why things are difficult. Okay, I know it's a bit of controversial. So this is an illustration. Suppose you're looking at this image, and suppose you're looking for a swamp. Okay, so you look at this piece and say, hey, that looks like maybe part of a swamp. Maybe that little corner here in the swamp, right? Do people agree? Okay, it's a reasonable guess. Right? So then you look around, okay, that's good. So we look around A, looking for it really is a swamp or not, right? You open another window, looks like, it looks like good because it looks like a neck of the swamp, right? Locally, I cannot tell B, but if A and B together, I can tell that's sort of a configuration like this, right? Again, the bigger the context, the better, okay? Okay, that's so far good. So let's open up a window again, so like a sort of a guessing game. You open up another window, look at this box C, and I say, wow, this is really good, right? I have 3 pieces ABC. It really all look like ABC here. So that's definitely a swamp, right? So how many people think it's a swamp now? Everybody, yeah. So it turns out it's not a swamp because you continue a little bit more. you find out that this image, if you continue naturally by the contour or similarity, it has some extra piece sticking out. Okay. So now what do we see? This is definitely not a swamp, right? There's a piece missing. So the big context, so with this I want to show that basically context is good, right? Because they help to recognize. But the context is also bad because if you take things out of context, then you can make a lot of make a lot of statements what this object is. So in this case, the whole context of objects A, B, C, D together. But if you just look at A, B, C, you think it's a swamp. But if that basically the false positives arise from the fact that you're taking things out of context. The A, B, C, D is naturally a bundle of contours that group together, or sort of thing has integrity, what I call it. There's a whole piece together. You cannot take half of it and make something out of it. So what is this? This is actually a cup. So what we saw was the, I think that was the swarm body and the neck. Okay. So we know this very well because we've been working on swarm detection. We found all kinds of false positives. We're looking into why, because there's always some piece look like a swamp. So swamps are everywhere. So if you don't look at things out of context, just zoom in, like just see this is a swamp, this one, you find lots of swamp. Okay. You had to look outside. Okay. Just look at the context to figure it out. So this is our motivation. This is our more latest work. It's not even published, but I want to talk about it at least. So the problem is that we have a very simple example of objects. In this case, it's swamp, but this swamp is actually just a line drawing. Okay, I want to show that we can do this. We don't need any more training example. Just one training example is enough, right? So frankly, I have 2 kids, so I just show them once what is a car. They know it's a car. So need more training example is not needed. So here's a problem. So we have a training set which consists of only one image for many training test sets, both positive and negative classes. What you want to do is detect this set of contour in the image in the clutter, meaning that so the clutter consists of all kinds of background contours, red and blue. We want to detect those blues are actually foreground contours. Okay, simple enough. We also want to be able to provide correspondence between the contours on the model and the contours in the image. Okay, so those are the correspondence labeled by similar colors are the correspondence between them. So we want to achieve 2 things. We want to be able to take this contour grouping results that we have, regroup it into an object which look like him, and provide dense correspondence inside the body. Okay. So this is going to do it for swarm and do it people. So this is just the starting of our work. So the problem is basically to find the right context. Okay, so we know that right context helps. Okay, the wrong context hurts because it makes you have false positive. So what is the right context? So here's actually the wrong context. So you're looking for swamp. Okay, so we detect here is a swamp. Why? Because it's a line lining straight up. There's another line that lined up. There's a line up. There's a line up. So majority line up. Okay, that's a swamp. If you think that's a swamp, you're going to have a lot of swamp because any L-shaped thing is a swamp by this measure. Okay, so why is it wrong? Because we are actually taking this contour out of context. We take a partial fragments of this long contour and declare that's a neck, right? We'll basically take somebody's shape and just chop up in the middle and make something out of it. If you allow the system to do that, you basically find many swamps. Okay, so here's another bizarre swamp. It's not really a swamp in the sense when you force a model to match a swamp in the image, typically what it does is find the best match. So this is actually a piece of rock, has a perfect shape of a swamp body, but no neck, right? But if you force the system to find the match, you will find the match somehow, but you don't know that's matched or not, right? So we want to be able to do that. We want to be able to tell from the matching whether something in the model is not matched, and we also want to make sure the match doesn't take things out of context. We want to find the right context to support each other, meaning that we don't want to say, hey, that's a neck, right? So this could be a neck locally, but this is not a neck without the body below. So the context is needed, meaning that you need to see a lot of things around it to figure out who you are, but you don't want to take the wrong context in. Okay, so that's the tricky part. So our problem is basically label those edges coming from the contour grouping 1, 0, such that if we reason about the ones, those are contours that collected, and we compute the shape as a whole of those ones selected, we can recognize what it is. Okay, just like the old woman, young woman. If you can tell me which piece that should go together, I can reason if that's the correct configuration. But you have to tell me that piece beforehand. Without that, I can't even reason the shape locally. Okay, that's the major argument that we want to put forth. So how do we do that computationally? The first I want to show that locally, this contour selection can be done very easily. Okay, well, not too hard, but at least. So imagine we're looking for a point on the swamp on this point. We want to figure out where it is in the image. Okay. So if we hypothesize the 2 points are corresponding, we can find out in the image which are the contours need to be foreground in order for me to match this shape with the swarm. Okay. What I'm showing here is a feature description called the shape context. So how many people know shape context? Okay. So shape context essentially is a description of a shape using a histogram measure. The histogram is defined by this log polar cells. So we count essentially each cell how many image edges is in that cell. Okay. We don't care where it is in the cell, we just count how many edge points in the cell. This translates into a description which is a histogram-like. So it tolerates quite a bit of deformation. So now what we want to do, probably cannot see very well, we put this same shape context on this image, and we will match with this swarm. Okay? And the background color look like this. So what I need to do is then locally select those right contours such that you can make this shape match with this shape. Okay, so these bright edges are the ones that selected from the contour for this point to match with this point. Okay, that looks good. So suppose we're looking for a second correspondence on this point of the swarm. Okay, we do the same thing. We're looking for this piece in the model. We figure out where there's an image. We need to declare each contour in the image on or off such that the shape context arrive on that look identical. Okay, this is, again, correct. Now suppose we're looking for a bud of the swarm, or the tail of the swarm. If you look at it actually locally, you could have a false positive like this, right? So this looks like a swarm, but you can see this context is inconsistent with these 2 points. Okay? So locally, we can define the problem contour selection is basically a variable x select, telling you which contour is on, which is off. And we have a histogram description for each of the points, in the sense that they will have a number of histogram bins and number of contours in the image. For each contour, we have one possibility of incidence between contour and bins. And what we need to do is select the right columns of those images such that we sum it up, meaning that select all of them, that description matches with the image, the model description. Okay. You can almost think of this as a complicated version of something called Earth's moving distance. How many people actually know Earth's moving distance? Okay, a lot of them, good. So essentially, you can think of there's a histogram here, which is coming from the image. You had to find a partial match with something that you know from the target. Okay, and in doing so, that you need to select which contour, and you can only select contour one in, whole out. Okay, and this is done by minimizing this equation, and this could be done in sort of LP programming. So that's the easy part. The hard part, as I can show here, is that locally, when you select the context sometimes are consistent, sometimes not consistent. Okay, you need to find a consistent context for everyone, and that becomes a much harder problem. It's a much harder problem because you actually solve 2 problems together. One problem is called a subgraph matching. Subgraph matching is that you have a model, you have an image, you have local clique potential to tell you whether things match or not. Itself is a pretty hard problem. The second problem is you need to figure out who's the foreground, who's the background. If you give a foreground background, you do the subgraph matching, but you need to figure out who's background, who's foreground first before you can do the matching. So you had to do sort of 2 problems together. But fortunately, there's actually a lot of constraints that tie those 2 graph problems together. And we won't talk about the detail of how to do it. Let me skip this one. So this is basically the challenge that we face. And this is some of the results we have. Again, this is a very simple set. This is the model, this is the contour, and this is the correspondence plus context we selected. So this is a false positive we saw before. We're able to match it, but the selection criterion was able to tell me that the model actually is missing the whole neck. So using the swarm to find the thing, but it will find the best match, but also at the same time tell you, actually, I didn't have the neck. I just find basically the body. Okay, so at that point, you can prune this false positives, right? A swarm without a neck is not a swarm. So, okay, so this is a more elaborate set of the results we were able to obtain. On the top left, we're showing a model that's used to detect image in the image. And we show basically the contour that being selected as a foreground as a whole, which match with the object on the top left. Here it shows essentially we're finding a bottle, right? The bottle has a lot of color inside and outside. It also is able to realize that somebody is occluding the left side of the bottle. Okay, tell you the left side bottle is missing. Okay, so the system is essentially selecting the contour in the image as foreground background, also selected the model contour as a foreground background to find the best matching between the 2. Okay, so we are able to do that. So the test actually is pretty challenging. The test consists of 5 categories of objects. It looks very simple: bottle, apples, and giraffe. And the test set is basically the entire set images together. You need to run the Borel image throughout the set. You don't know if it's a Borel image or Doral image. And what you're looking for is precision recall. So you want to make sure that when you do the Borel detection on the giraffe, nothing fires, right? You don't want to see Borels in giraffe, or vice versa. So here's a bigger set, and this is a sort of you can think of some of sort of failure modes. This is a Apple logo looking for a cup. So you find the match of the half Apple logo, but it also telling you they're missing a byte. Okay. So at that point, you actually can post-processing and prune it out, saying that's not a match. Here's basically a cup looking for actually match to a bottle, but it's also said the handle of the cup is missing. So you can also prune out later. This is actually a cup, bottle looking in a giraffe. You find the lower piece of the bottle, but they tell you the top part of the bottle is missing. So this is a really bad false positive. It found the head of the swarm and no neck and no body. Again, same thing. This is unfortunate. She looks like a bottle from that distance. And this is the sort of the swarm problem that I mentioned, the accidental alignment that we see quite often in image. So this is one of them. So I think actually I probably should quit at this point. We have a lot more results to show. Let me just show one more result. This is some latest thing that we're doing on a collection of a Chinese emperor database, where we have an entire set of facial images of the Chinese emperor tombs. And those are the contours, and what we want to do is extract facial features from those. So it's extremely difficult set because there's no color features we can use. The edges are pretty messy. So it was doing pretty well. So we're able to detect the nose, label them into eyes, nose, mouth, and select those contours from those images. So I will probably conclude my talk here. So let me fast forward and just point out that the work is done actually with a big group of students at Penn, and except this guy who's not from Penn, but he's very helpful. So this is Alisha from CMU. All right, so that's my talk. Questions? I can show more face images while we. So this is another set of face images. Again, those are a big collection of face. What we want to do is be able to detect those facial features from a pretty badly cluttered scenes. So this is, again, we're looking at the contours and remove clutters from that contours. Okay. All right. Yeah, Dennis.
So I guess it's your second to last slide, the one before this example where you're looking for swans and mugs and things like that.
Yeah.
So your approach to detecting the clutter is kind of independent of the task that you're doing, but that slide really suggests that, if you have the model of the swan and the bottle and the mug and the apple, the salient contours really should be the ones that are kind of relevant for the task. And I was wondering if you have any plans to kind of incorporate close the loop that way.
It's a good question. Yeah. So the question is, if I'm not looking for a swarm and bottles and Apple logo, the saliency of a contour might be different. It's definitely a good point. I mean, in some sense, the two are somewhat related. You can think of a random walk, right? So when we do the contour grouping, we're doing a random walk with a state machine of two states, forward and backward. Okay. When we do the swarm, actually, we can think of essentially the state machine enriches, give you a little bit more features, like the neck of the swarm and so on. You actually can design potentially a random walk in this finite state machine space that actually is very similar to what we're doing here in this guessing game. In this guessing game, you can think of when you do this random walk, you can actually think of this as a random walk. You start with your state, and you associate this thing with a state, which is the image model. And in which the second state, you actually re-enriched both state, and you use random walk. And when you see a contradiction, you have to backtrack. So you can think of this as actually a random walk in some finite state machine, trying to prove this object exists. Yeah, but the random walk concept is a little bit complicated to do in that state machine, finite state machine concept. Yeah. So you can think of, and sometimes I think this is sort of object recognition by proof, right? In order to prove this is an object, I need to find all the consistent subset. I need to propagate this proof out. And when I see a contradiction, I need to backtrack. And what I'm looking for is a salient sort of set of mutually consistent evidence support pairs.
problem with that view, right, is that if you have just a single model they're looking for,
Right.
you can be very myopic.
Yeah.
And so you could say, okay, I'm in the image space, and I also have my state consists of a pair placed in the image space, and the place in the contour of my model.
Right.
And then you just kind of have some transition function
Right.
that is governed by where you can go in your model, which
Right.
is
Right.
uncluttered
Right.
and
Right.
but that's sort of too easy, right? Because
You can find that.
if you don't know whether there's one there, but maybe there's a rock, so
Right.
you would have you could be deceived.
Right, exactly. Positives, yeah.
Yeah.
So we want the saliency of the contour not to be destructed. So in order later work, we say, okay, do anything more, but don't destroy the native contour grouping. Basically, they are grouped together. There's no reason to pull them apart. There's no object that can saw in the middle of the contour. So, yeah.
Have you thought of training how to group these contours? Because say you have this natural seams,
Sure.
you have the soft curves, not too much angular
Sure.
things, and then some things you like, say indoors you have
Yeah.
boards, windows, straight angles, whatever.
Right, right. But this is come back to the same thing again. So you need this sort of a context in order to set up the weight matrix or the random walk a little bit better. And the context depends on you able to figure out who's belonging together to begin with. And that's sort of create a very sort of chicken egg thing, right? You need to know who your buddy to see the context. And then it depends on this context to do something for you. So if you pick the wrong context, you will do the wrong thing. So that's the thing you have to resolve. How do you know you're in the right context? Yeah, Andrea.
I think I missed something in the details of how you actually go from the shape contexts to
Right.
To
Yeah.
verifying all these pieces. And what I'm kind of left wondering is what do you get out of doing this over the iterative shape context matching and deformable template approach
Right.
from Boulanger and Malik?
Right. So in the Boulanger and Malik, what they did is that they do the local shape context matching using the whole window, and then do the deformation. So the thing they are trying to address is the model is deformable from the image. What they are not addressing is the shape context has information. So in that case, the shape context is big enough, and there's no clutter around it, right? So usually the clutter is removed. So in the case you already kind of have a nice foreground object in front of you. So you can use the shape context to tell you where you are. You can increase the shape context window to really tell you where you are. Our case is that we don't have the background removed. The clutter is there, okay? And the clutter is the one that makes problem hard. If you already had a foreground object grouped, that becomes basically what I said is a graph matching problem. So you just need to find the correspondence between the two graphs. That's what they did. The problem is I don't know which one is the foreground, which one is background.
You can't solve that by doing some of the
Iteration.
earlier contour finding first, or putting that in the loop.
We already did as much as we can. We find all the contour out. I mean, those are salient contours. They're just not swarm. They could be something else, just not the object I'm looking for. Right. Good question, yeah. Yeah, so in fact, I was very motivated when I was read the shape context papers. Oh, that solved everything. But immediately when I tried it, opened the shape context up, for articulate object like a human, majority of things on the background. If you have points on the body, the most of the point will be on the background. Okay, so the 50%, 60% of your signal is corrupted. You couldn't get any reasonable alignment to begin with. Okay. Yeah.
Do you have any results to show for the human pedestrian detection?
Not yet, not yet. I mean, we have results on the sort of, I have a slide somewhere. I don't know, so I think I shrunk the slides quite a bit. Let me see, where is it, if I have one. Okay, maybe this one. Yeah, so this is the false positives that we, doesn't do it, okay. Go to the end, and now hide this. So for human pedestrian, this is a typical false positives, okay? So this is a model of a pedestrian, and this is the false detection. Okay, what happened is it declared this is the head, looks good, right? It declared this is the leg, because locally, if you don't see the context of this, you find the two vertical lines, we just line up with that leg. Okay. At that point, you find the head, you find two legs, you say, hey, that's a body. So you put a bounding box here in the middle, say that's a body. That's a typical false positive. Okay. Again, it's taking things out of context because locally this two parallel line looks like a leg. This two parallel line look at another leg. Two legs, one head, that make a pedestrian, usually. But in this case, you see your leg actually go all the way out. Unless you have a leg look like this, that's not a human. So you're taking things out of context. And here's another false positive. So you call this is the left side of the torso, that's the leg. You call this right side of the torso, that's a leg. Okay, left side torso, right side torso, two legs, that's a human. So again, you put a human in the middle of it. Okay, this is again taken out of context things. So our strategy is for the pedestrian is not just looking at contours, we actually can use region segmentation. And our goal is trying to piece those segments together such to look like a red line, which is a pedestrian. And for the false positive, for example, we found lots of clutter. Basically, it finds a vertical edge, lots of edges that line up. There's a people here. It says, well, that's the lower body of a human, giant, okay, standing. But if you look at the edges, they all line up, okay. So again, we use the idea of using a region as a basic element to select them, try to find a combination of the segments of the regions that actually can be look like this person. But when you did that, it turns out there's nothing can be selected, meaning that if you select them, you gain somewhere, you're going to pay a huge penalty somewhere else. In the case of this one, if you gain this piece, you're going to pay a huge penalty for this because it doesn't have a correspondence. That's why we force both correspondence and the segments together. Again, if you take this left side, if you force the segments, is either you put both segments together, that's a human, double human. You can take basically half the thing out. So you can't piece the segment together. So segmentation is not perfect, but the combination of segmentation actually is close. But the problem is you don't know which combination to pick, and this is where the model-based way piece them together. Yeah.
So would you say your technique for detecting the salient contours is independent of resolution? So for example, you're shown an image where there were buildings, one was in the front and one was behind, and it didn't detect the windows, and the smaller windows. So if you zoom in into that image, will it start detecting the windows or will it still ignore them?
So the windows are particularly a problem because what happened is essentially zigzagging. It could be zigzagging. And when it's zigzagging, it really destroys the saliency. So if you really want to get a windows, then you need to be sure the random walk goes straight or goes straight up and down. If you start zigzagging, you start losing the saliency.
Well, but if you zoom in, then it would be similar to the windows on the left, where each
but the
window
window on the right, you
detected,
can see there's actually no zigzagging, it goes straight. It's a grid versus a line. Okay? So yeah, we need to get this grid out. I mean, we do want to get this grid out, but that requires understanding there's might be two crisscrossing random walk together. Again, we have to enrich the state machine. The state machine needs to recognize that there's a state called the crossing, where two random walk had to cross.
Well, but it could also detect just a single window.
Oh sure, cycle can
right?
cycle, but you get confused because there are many possible cycles to go on.
So the thing, I mean, pushing on that point, I mean, it's a matter of the sort of the resolution, right?
Sure.
Because your jump probability maybe is not attuned to the depth.
Right.
So it's you for that image you should have those windows you have a much lower jump probability. You know, the distance, you should penalize distance a lot more because that's a sort of a background, and you would say for the foreground.
Yeah, it's true. But we had to distinguish, for example, a regular grid versus, let's say, this kind of chaotic grid, right? So there's a difference between this regular grid and the clutter. Because if you zoom in, you say you want to enhance every connection, then everything will come out. So you still need to make sure that to me, this is more regular texture. A regular texture has additional property as compared to sort of the clutter texture.
It's a question of regularity. It's a question. I mean, you could get the nice contours for each of the windows, right? If you have.
Yeah, but you can't.
If you were close, you know, the problem is that you're allowing yourself to jump over from window to window because you are too willing to jump gaps.
Sure. I mean, you can think of a random. I mean, the eigenvector is trying to find a common explanation for many things at once through this random walk matrix. If you can synchronize all the windows together, it will pop that out. But it's not going to do one window at a time because then it's wasting a lot of energy to do one thing. because the eigenvector really find the majority modes. So it's not going to find the modes if you're doing one at a time. So you have to make sure all of them actually are synchronized together. So it could be because they have the same length. But that alone is not enough, because there are many things with the same length. You have to some geometry inside. So eigenvector is essentially trying to pull out the majority of the image which share some common concept of random walk. And unless it's very salient, it's going to pop out. Otherwise, it's trying to share them as much as possible. So, yeah. Yeah.
So if you were to, for example, incorporate some appearance information and somehow attach it to the edge, would this end up kind of changing the setting of your graph? Could you make it as a part of the activity?
Right. I think Jean-Yves was saying that before, that we changed the polarity, using a polarity for edges, right? If it's dark to white transition, I want the next one also dark to white. It's going to gain you somewhere, but sometimes it's also going to hurt you because I'm standing behind some background. You really don't know the contrast between the background and the foreground. So, yeah.
How about the detection stage?
Yeah, I mean, it's definitely, this is the thing I go back and forth. When you do look.
You already have the model, and if you would have something else than a contour.
For face, for natural human face, right? So polarity definitely play a role. So, we don't see inverted face quite often. I mean, there's a polarity, regularity between the facial features. The eyebrows tend to be, white to black or so on. But for general objects, like human pedestrians, it will be really hard to. I mean, it could be that there might be subcategories of body shapes or clothes with, some foreground background color. But it's hard for me to think ahead.
Per contour, but the neighboring contour should have the same appearance, so then you increase the probability of jumping to the ones which.
Yeah, I think that definitely, let's open up the question of learning. So I think that's a place where I'm pretty happy for the machine to figure out. Yeah, and I don't know the answer to that. Yeah, it's a good question. Yeah.
Use a regular canny filter to start the process.
So I forgot to mention that. So we don't use canny because the canny actually is below PB. So PB is the probability of boundary detection. This is the detector that came from Berkeley. They're actually pretty good. They're about 10% above canny. So.
How do they do in corners? Do they actually capture corners as well, since canny doesn't?
I think they all die as a corner. Corner is the biggest headache that I have, yes. All of us struggle with corner.
Why don't you combine your corner detector?
Yeah, we are trying to. I think actually Jitendra has a paper just in this CVPR looking for corners, and they were pretty good, combining segmentation with the corner detection. So a corner is a big headache because a corner is a junction, and a junction has a meaning, occlusion usually, and need to figure out whether to jump across or not. Yeah, we thought a lot about this. Yeah. Good question. So I hope the messages you get home today is that contours are very useful. I shouldn't ban them from images, and we are able to get those contours out. The second thing is that contours grouping together in the right way provides you a lot of information of the shape, a much bigger global shape, rather than just local contours itself. And the message is really try to sort of a subtitle of the talk maybe is get away from patches and move into this geometry. I know it's a big controversy, but I think we can make a strong argument that you need very few training examples in that case to verify. You don't need a lot of training examples.
Okay, thank you.